Now we start talking about an example. This example is called the standard template determined by 2 points. So now given 3 points, given 3 non-negative numbers, t0 which is strictly less than t1, which is strictly less than t2, and the integers m, n, d with d equal to m plus n, and those 3 non-negative numbers satisfy the relation t2 minus t1 divided by t1 minus t0 equal to m over n. Now we'll construct a template. Recall that a template is a vector-valued function from the non-negative real numbers to Rd. And f has d components denoted to f1, f2, all the way through fd. Now we'll describe this template. Now we'll construct a template by a graph. This graph, here's the x-axis and the y-axis. Is 0, t0, t1, and t2. f1 lies below, and f1, f2, and f2 through fd lie above, and they should satisfy the equality that f1 plus the dou fd is always constantly 0. And now we will add slopes to those piecewise linear functions. The slope here is negative 1 over n. Slope here is 1 over m. The slope here is 1 over n times d minus 1, and slope here is 1 over m times d minus 1, negative. Our next goal will be to compute the quantities given in the definitions above. So L plus minus M plus minus S plus minus delta, little delta, big delta, and the lower and upper average contraction rates. And we should observe, here's the observation. There are only 2 intervals that we need to worry about in the computations. The first one is from 0 to t1, the second one is the interval from 1 to t2, t1 to t2. They are intervals where f1 is strictly less than f2, and that f is linear on those intervals. And we should also note that f0, which is by convention negative infinity, is strictly less than f1, which is strictly less than f2. But f2 is equal to f3 and all the way to fd, which is strictly less than fd plus 1, which is by convention equal to the positive infinity on this whole interval of support from t0 to t2. The first thing we need to do is to determine L plus minus, which is the quantity that depends on F and I sub I, Q, where I is equal to 1 or 2. And this is an integer from 0 to d plus minus. Remember, d plus is m and d minus is n by our assumption. And now we need to determine what q we can choose. Remember, in this definition, this q is an integer from 1 to d such that fq is strictly less than fq plus 1 on some interval. So in our case here, q can be only chosen as 0, 1, or d by the inequality here. So now we divide and conquer. First, if q is equal to 0, then by our definition for L plus and L minus, remember, by our construction, L plus and L minus is determined by a system of two equations, and what you need to do is to solve those two equations for L plus and L minus. And in our case here, the first equation will be L plus L minus, which is q, which is equal to 0. And the second equation is that f0 prime, which is 0 by our convention here, and this is supposed to be equal to L plus divided by m minus L minus divided by n. Solving those two equations yields L plus equal to L minus equal to 0. So this is our first case. The second case is that when q is equal to 1, in this case, L plus L minus, which is q, is equal to 1. And the second equation says f1 plus is equal to L plus divided by m minus L minus divided by n. But f1 plus here will be simply f1 prime. And f1 prime has two possibilities. Remember, in our construction here, it can either be negative 1 over n or 1 over m, 1 over m. So here, it would be either negative 1 over n on I1 or positive 1 over m on I2. So if you solve those two equations, you will get two possible solutions. So first, if the interval is I1, then you get f plus L plus is equal to 0 and L minus is equal to 1. So this is on I1, but on I2, you get the opposite. L plus is equal to 1 and L minus is equal to 0. Okay, now case 3. When q is equal to d. So in this case, L plus L minus is equal to q, which is d, which is further equal to m plus n. But the second one, which is fd prime equal to L plus divided by m minus L minus divided by n. So this guy, by our assumption, is always 0. It's always 0. And if you solve those two equations, you will get L plus equal to M and L minus is equal to N. This is the only possibility. So in the case 1 or case 3, so this holds for both I1 and I2. What we just computed can be summarized in the following table. Now, in the second step, we'll determine the interval of equality for f on I. Now remember that we have the following inequality. And recall the definition. So here's the definition for the interval of equality, which is an interval of integer values such that this holds. Now you can easily see from here that there are only two possible intervals of equalities. 0 to 1 intersection Z and 1 to D intersection Z. In the first case, there's only one number, just 1. In the second case, you get 2, 3, all the way to D. In the third step, we compute M plus minus PQ, which is a number that only depends on the F, I, P, Q. What we will do is that we will use this table. M plus of I1, 0, 1 equal to L plus I1, 1 minus L plus I1, 0, which is based on the table above, is 0 minus 0, which is 0. And you can compute the rest directly using the table above. So this completes the third step. In the fourth step, we will use the information above to compute S plus of Fi1 and S plus of Fi2. Remember, there are intervals of integer values. By definition, S plus of Fi1 is the union of over those interval of equalities of those intervals P from P to P plus M plus I1 P Q intersection with D. Note that in this case we actually only have two possibilities. Why do we have two possibilities? We did this in our second step. So there are only two possibilities. So first one is 0 to 0 plus M plus I1, 0, 1. Intersection with Z, union, the second case is 1, 1 plus M plus I1, 1, D, Z. And this is In the first case, the first set is really just the empty set. This is just the empty set because m plus, we just compute m plus is just 0. So this is the empty set. And the second one is from 1 to m in the section with z. The second one is just 1 plus this m plus of I11D is computed in here, which is m. So what we get at the last are the integers 2, 3, all the way to 1 plus m. And you can similarly compute s plus of f, I2. And this yields the integers from 1 to m. In the fifth step, we compute delta of f1 and delta of f2. Remember, this is defined as follows. Defined to be the number of pairs I plus, I minus is the product of s plus and s minus, where I plus is strictly less than I minus. This is the definition. And we also recall that S1 and S2 are disjoint, and their union is precisely the integers from 1 to d. So you can easily use the information we just computed to conclude that delta of f, I1 is equal to mn plus mn minus m, and delta of f, I2 is equal to m times n. And finally, we can compute the capital delta of f, t0, t2. Remember that this is defined by the integral average, where the integral is from t0 to t2, and the integrand is the little delta we just computed. This is a piecewise function, constant on each interval, I1 or I2, and you plug in the information above and compute that this integral is equal to mn minus mn over m plus n. And remember the lower and upper average contraction rates defined using the lim-inf and lim-sup, as in here. So in this case, because this f is supported in here, and because it is a essentially this delta is a constant when the T blows up. So what you get about the lower and upper average contraction rates are just the same constant computed in here. So does this look familiar to you? Yes, it should, because this is precisely the Hausdorff dimension we want to compute from the beginning.